Hello friends, there is one more topic is there from engineering mathematics to differentiation under integral sign. There is a two rule from that we by that rule we can differentiate any integral function. So let us see how. Rule number one we have, if I am considering integration I of a is equal to integration some alpha to beta f of xa dx. This is one of the integration we have. While integrating this quantity you will get a function of a, and hence I am denoting it as a I of a, where alpha and beta both are constants. Alpha and beta are constants. So the differentiation of this become d by dA of I of a, which is equal to I dash a, which is equal to differentiation of this. So as alpha and beta are constant quantities, we are just partially differentiating this f with respect to a, so it become alpha to beta dabba by dabba a of f of x comma a dx. This is what we have rule number 1. On the basis of this rule we are solving some problems. So considering first problem, show that integration 0 to infinity e raised to minus x minus e raised to minus ax upon x into sec x dx, which is equal to 1 by 2 log of a square plus 1 upon 2. Fine. Now so I'll consider this integration. Fine. I of a is equal to integration 0 to infinity e raised to minus x minus e raised to minus ax upon x sec x dx. Considering that integration, if you go on integrating this you will get a function of a only, because we are after integrating this you can put upper minus lower and whole quantity become in terms of a only. Fine. Now as if you look at that integral, that is not easy by whatever rules we have in a definite integral. So by default we have to use the differentiation under integral sign. So let us see how that works. So differentiating both the sides with respect to a by using differentiation under integral sign DUIS. So it become differentiation of this is I dash a, which is equal to integration 0 to infinity partial differentiation with respect to a e raised to minus x minus e raised to minus ax upon x sec x dx. So therefore differentiating it with respect to a, this quantity is a constant. Integration of e raised to minus ax become e raised to minus ax into minus x, so which is equal to integration 0 to infinity as it is, this becomes 0 minus e raised to minus ax, and differentiation of this become minus x upon x into sec x dx, which is equal to integration 0 to infinity minus minus become plus x e raised to minus ax upon x into sec x dx. This x's get cancelled now, which is equal to 1 upon sec is a cos, integration 0 to infinity e raised to minus ax 1 upon sec is a cos x dx. So we will use this formula, e raised to ax cos bx dx is equal to e raised to ax upon a square plus b square into a into cos bx plus b into sin bx. We have this formula. So by that formula we are writing this integral as e raised to minus ax upon a square plus 1 square into minus a cos x plus sin x. Fine. And from 0 to infinity upper minus lower. Now here value of a is minus a and value of b is coefficient of x is 1. So accordingly we are writing integration. Upper limit e to the power minus infinity becomes 0. So 0 minus lower limit e to the power 0 is 1 upon a square plus 1 cos 0 is 1. So minus a is there, sin 0 is 0, so plus 0, which is equal to minus minus become plus a upon a square plus 1. Now this quantity is I dash is equal to this quantity. Now we required I of a, so I'm integrating on both the sides. So integrating on both the sides with respect to a, so it becomes integration I dash a dA, which is equal to integration a upon a square plus 1 dA. Integration derivative get cancelled, fine, so it become I of a. For this derivative of a square plus 1 become 2a, so I am adjusting 2, multiplying by 2 and dividing by 2, so which will be equal to integration of this 1 by 2 log of denominator, that is a square plus 1 plus some constant of integration c. Now I am calling this as a equation number 2 and this as a equation number 1. Now therefore first I'll put a is equal to 1 here in equation number 1. So what it comes, let us see. Put a is equal to 1 in equation 1, so it become I of 1, fine, putting a is equal to 1, so it becomes 0 to infinity e raised to minus x minus e raised to minus x upon x sec x dx, fine. E raised to minus x, e raised to minus x get cancelled, so integration of 0 to infinity 0 dx, which will be equal to 0. So therefore I of 1 is 0, fine. Now we already get that I of 1 is 0. Now in the same way I will put a is equal to 1 in equation number 2, that is here 1 and here 1. So put a is equal to 1 in equation 2, so that become I of 1 is equal to 1 is here, so 1 by 2 log of 1 square plus 1 plus constant of integration c. 1 plus 1 is a 2 and I of 1 is 0, we already have, so 0 is equal to 1 by 2 log of 2 plus constant of integration c. From this we write the value of c is equal to minus 1 by 2 log of 2. By putting the value of c is equal to minus 1 by 2 log 2 in equation number 2, we write equation 2 become I of a is equal to 1 by 2 log of a square plus 1 minus 1 by 2 log of 2. So by laws of logarithm we write 1 by 2 log of a square plus 1 upon 2, and this is equal to RHS, that is integration 0 to infinity e raised to minus x minus e raised to minus ax upon x into sec x dx is equal to 1 by 2 log of a square plus 1 upon 2, hence proof. Now considering one more problem from differentiation under integral sign. So evaluate 0 to 1 x raised to a minus 1 upon log x dx. Integrating this you will get a function of a, so I am considering I of a is equal to integration 0 to 1 x raised to a minus 1 upon log x dx. Now directly we cannot integrate this quantity, so differentiating both the sides so that we get some quantity and we can integrate easily. So differentiating both sides with respect to a by using differentiation under integral sign, so it become I dash a is equal to 0 to 1 partial differentiation of this quantity, so dabba by dabba a of x raised to a minus 1 upon log x dx, which will be equal to 0 to 1. Before that I am considering this as a 1. 0 to 1 x raised to a differentiation x raised to a log x, and once a differentiation are 0 upon log x dx. Now this log x get cancelled, which is equal to 0 to 1 x raised to a dx. Integrating this, you will get x raised to a plus 1 upon a plus 1 from what? 0 to 1, upper minus lower. So 1 raised to a plus 1 minus 0 raised to a plus 1 upon a plus 1. 1 raised to anything become 1 only. So I dash a is equal to 1 upon a plus 1. But we required I of a. So integrating on both the sides. Integrating on both sides. Integration derivative get cancelled. So I of a is equal to integration 1 upon a plus 1 dA plus constant of integration c. 1 upon, so integration of this become log of 1 plus a plus c. I of a is equal to this, calling this as a 2. So therefore we wanted to find the value of this constant c. For that purpose I'll put a is equal to some constant here, so that this integral become 0. Now if I put x is equal to 0 here, sorry, a is equal to 0, so x raised to 0 is 1, 1 minus 1 becomes 0, and value of the integration become 0. So that I'll put a is equal to 0 in 1, implies that equation 1 become I of 0 is equal to integration 0 to 1 x raised to 0 minus 1 upon log x dx, and x raised to 0 is 1, 1 minus 1 becomes 0, so I of 0 is 0. Fine. Now similarly we are putting a is equal to 0 in equation 2. So put a is equal to 0 in equation 1 implies that I of 0 is equal to log of 1 plus 0 plus c. Log of 1 plus 0 is log of 1, and log of 1 is 0. So and I of 0 is already 0 plus c implies that c is equal to 0. C is equal to 0 putting in equation number 2. So equation 2 become I of a is equal to log of 1 plus a, hence the value of that given integral.